afternoon and welcome to this course. This is mainly for UK students who are taking A-level maths, and this is for year 13 A-level maths. In this particular course, I'll be covering differentiation in the first half, and in the second half, I'll cover integration. Uh, just the preliminary knowledge about year 12 mathematics is necessary. I won't be covering that here, but I briefly explain some of the more difficult concepts. But if you haven't done A-level mathematics, that's fine. This course also applies to students who are doing IB program and any other English-based mathematic programs uh, that requires calculus. Let's get started. This is the content of the first half of the course. So don't worry, it doesn't involve any integration quite yet, but I will be covering that in later chapters. So you are more than welcome to fast forward to any particular uh, video that you wish if you don't require uh, this current video. So in the first video, I'll be covering the differentiation of sine and cosine functions from first principles. So let's get started. Okay, so in year 12 we learned that the derivative of a function gives us a function that can calculate the derivative at any point, any x value that we are given. So where did that come from? So if we take any of these 2 points on the graph, for example, and label them x and f of x, the lower value will be x and the f of x will be its y value, and the second one on the top right corner would be x plus dx, and its y value would be f of x plus dx. And from first principles, you should be familiar with this formula where we are going to take the limit as dx approaches 0 of this formula. Can I just briefly point out that here this is x plus dx, that's this coordinate here, and when we take away this x here, these two cancel away. That's why we don't bother writing those two x's. Okay, so applying this formula, we have to be very careful and always write the limit of x going towards 0 in front of each and every line. Mathematics is funny that way. They do want you to show that you are using a limit. So in the exam, this is very necessary to write this limit of curly x. I sometimes use just the normal d, but dx, but it's better to use the best uh, writing, just not to get confused. All right, so we're gonna apply it to an example of a function like x squared and see why is it that it'll give us the answer comes out to be 2x. All right, so let's have a look. So when f of x here is x squared, so what we're going to think about as this f of x, this bracket, everything here is going to be replaced with the x squared. So if I write it by hand, limit of curly x going towards 0 of x plus dx here is going to be squared, and we're going to subtract the f of x, which is x squared itself, and that all divides by delta x. Actually, that's the name for this curly d. They call it delta x. All right, so When we expand this bracket, we're going to have x squared, two lots of delta x multiplied by x, so not to get confused, and the delta x itself is squared, and we are subtracting x squared, and this d is the same over here as that d here. So if I keep the same notation, these x squared at the beginning and the end of the numerator cancel each other out because they're adding and subtracting, and then we can split this fraction up. As I said, it's important to have written this dx going to 0. We are taking a limit on every line here. So then we can say that we have 2. I'm going to bring this x at the front and have this dx at the end here. This will cancel away and in this fraction, and I'm splitting the numerator up. And we actually have a negative rather than a positive, my bad here. And this dx remains, this is squared and this is not squared in the denominator, so that will cancel away. So the very first term actually doesn't have any delta x left in it. So as delta x approaches 0, this 2x remains as it is, and here we will have a single delta x which will approach 0. So that limit finally, now that in this first term we don't have a delta x, we can go ahead and take the limit and say that remains as 2x, and this will approach 0. So we don't have to write anything next to 2x. So therefore we can say that we were, all this time we were finding the delta dy by dx here. So our dy by dx is 2x. Sometimes you might be familiar with this notation f dash of x as well, which is one and the same thing. Okay, so let's uh, let's have a look at this again. Alright, so here's a refresher for just applying the power rule without differentiation from first principles. Just to warm you up with the power rule, here is everything you should remember from year 12 maths. So if we have to, if you haven't done this, I recommend you pause the video and have a go at it before I show you the answers. Okay, there you go. So if we want to differentiate using the power rule, we know that this power is going to come to the front and multiply with the 3, and we are going to have 6x minus 5. X to the power, we can read the minus 5x as x to the power of 1. So 1 times 5, and then subtracting 1 from 1 will leave us x power of 0, which we don't have to write. So 6x minus 5 is the answer there. I recommend my students to rewrite this as, first of all, the question itself as x to the power minus 1, and write this as x with the power of a half. Then you apply the power rule and you should get negative 2x to the power of minus 2 minus half a x with the power of minus a half. So this will be the derivative dy by dx. For this part b would be negative 2x to the power minus 2, take away x to the power minus half to the half at the front. That these powers, negative powers, you can put them in the denominator and write them as positive, like the answer given here. Now for this part C, I'll recommend uh, you can multiply the bracket first if you're not familiar with the product rule, which I don't expect you to do. When we multiply the bracket, we are going to have 4x squared minus 4x to the power of 4. Then we apply the power rule. And it's important, you're right, that we are taking the derivative. Don't confuse this top line with this line here. There's a whole different thing, these two lines. Uh, they are very different. So we're going to have 8x with the power of 1 minus 16x to the power of 3. So that would be the answer there. Now for part uh, question B, question 2 here is saying the equation of tangent is find the gradient. But we're going to have to find the equation of tangent. This is basically, if we try to sketch it, it's a negative quadratic, uh, and it's asking us to figure out at a particular point where x value is 3, we actually don't need the y value here. What is the equation of the straight line? Tangent is something like that. So the question is asking us to calculate that, and to do that, first we need to figure out the gradient of the straight line by differentiation. So we're going to say dy by dx is going to be negative 2x, and we're going to evaluate this expression when x equals to 3. So when we substitute 3 there, we'll have negative 6 as the gradient. So at that particular point, the gradient is negative 6, and you should be familiar with this equation. To figure out the equation of straight line, we usually use this expression where we can replace y naught and x naught with the values we are given here. So these two come from there, and the minus 6 is our gradient, which we label m. So substituting that into the formula, we'll have a minus and minus 1, negative 6 here multiplied by this x. First x is part of the equation that doesn't get replaced by anything. The x value is 3, so we have y plus 1 equals to, first I'm going to multiply the bracket here. Negative 6 times 3 is a positive 18, and I know that there is a plus 1 on the left hand side, so when I bring it to the right, it will be a negative 1. So the final equation should read as negative 6x plus 17. Now I'm gonna rub my working out in a minute, and because actually um, there seemed to be a mistake here. So when we replace our negative 6, um, negative 6 multiplied by minus 3, that minus is part of the formula, so I'll look into that. I think there is a mistake there. But I've managed to correct that. So the next part of the next question is asking us to find from first principles what is the derivative of x cubed plus 2. Let me get rid of the writing, my handwritings here, so that we can see the question better. So um, now I've put this question myself over here just to challenge some of you. So if you remember, dy by dx is the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So we're going to use this formula over here. So we'll have limit as x delta x approaches 0 of I'm gonna open a bracket. The 2 doesn't have any x in it, so I'll write x plus delta x here, cube, plus 2. This 2 doesn't change because we cannot add a delta to it because it doesn't have any x's in it. And the function itself is x cubed, if I write it in a bracket, plus 2. Alright, all of that, I'm going to write dx as a denominator on that side over here because I want to leave a lot of room here for my writing as delta x approaches 0. Expanding the numerator, that bracket, I'm going to use binomial expansion. And if you are familiar with the formula, we'll have 3x squared single delta x here plus 3x delta x squared, and finally we'll have a delta x cubed here plus the 2, and now I'm gonna basically multiply this negative sign into that bracket. We'll have a negative x cubed minus 2. So you can see clearly this plus 2 and a minus 2 will cancel, and this negative x cubed will cancel away the front x cubed at the front. So if I just highlight the cancellations with purple over here, so these terms cancelled away. Oops, sorry about that. So, and don't forget that we have a denominator that is delta x. Now we can look at the rest of that. So again, we are taking a limit as delta x approaches 0 of this expression. So I can tell by looking at this expression that the delta x will cancel away. Uh, me from the future. Sorry, I missed the square here. On this step I missed out. There was a square here which I forgot to put and carry over onto the next line. So my apologies. Please put that square on top of the x for your future reference. Million, that will cancel away. All right, so take a break if you wish. Now we are looking at the derivative of sine and cos. So you should take this for granted that at this stage, when we take a limit of sine of theta divided by theta, as theta or the angle approaches 0, this expression will approach 1 because the gradient, as you can tell by the graph here, the gradient of the blue line is 1. Okay, so we're going to use this assumption and one more assumption that cos of theta will be given to us by 1 minus theta square over 2. These assumptions come from chapter 5, I believe, of the book. So when we look at the radians, look at angles in trigonometric with radians, we will have seen the proof of these already. For small angle approximations, these are the true values. Okay, so we're going to use these uh, assumptions and the other trigonometric assumptions that are appearing on top of the board in our working out. If you're not familiar with these, I intend to create another course on trigonometry and show you where those formulas come from. But for the purpose of this exercise, we are going to take them as given to us. All right, so let's have a look at this expression. We looked at the sine of theta. Uh, divided by theta as theta approaches zero. Basically, in chapter 5, we learned that we can, for a small angle approximation, we can replace sine theta with theta itself, and theta divided by theta will be 1. No matter how small the angle is, it's still going to give us 1. All right, and this is the graph of uh, cos, cos theta that I've provided on the bottom left corner, and that's another proof that why this will be given. That's why uh, we we say that the cos of theta itself, when we take away 1, its value will cos of theta will be 1 at 0, but 1 minus 1 will give us basically numerator of 0, and 0 divided by theta will be 0. Uh, you can apply more better mathematics if you apply the L'Hopital rules, but that's beyond the scope of this course. All right, so we are going to have a look at why the derivative of sine of x or sine of theta is going to be. I don't want to spoil the answer, but it will be another trigonometric function. So let's see. With double angle formulas, we can replace this sine of x plus h with basically sine x cos h plus uh, cos cos x sine of h. All right, so this section here, this is the expansion of the underlined bit here. Okay, and the rest is just copied the rest as the line above. So now we can do some rearrangement because we can factorize the sine of x out of the first two. Basically, I wrote this term here first and I put that term at the back. So we can factorize the sine of x there, and uh, maybe we can factorize something else. Yeah, when we factorize the sine of x, we'll have cos h minus 1 in the bracket, and the second function, we are just gonna take it as 1, right? So that's we said that we can make the assumption there, and here we are saying that this part of the expression sine of x gets multiplied by 0 because there's a 1 minus 1 inside the bracket there, and that will approach the whole section here will approach 0. So that's why we will end up with the derivative sign being cos of x, right? Okay. So this is one of the next question to prove from first principle what is the derivative of cos itself is an exercise in your book that you should have a go first before watching the rest of the video. So I suggest you have a go at this question here. If it's not clear, we are going to differentiate cos of x from first principles, right? So have a go at it and then have a look at the rest of the video. All right, so it goes like this. We're going to replace the first x plus h, and wherever we see f, we're going to replace that with cos. And then we're going to have a, if you haven't seen this already, you can use this expression here. This is given to us on top of the page there. So we can write the limit of h approaching 0 first at the front, and we are basically gonna use x and h as two different angles. So cos x multiplied by, don't read this as cos, there should be a bracket around each of these values there. So then we can see that this term here, cos x, has something in common with that negative cos x. We can rearrange this, bring them together on the next line so that we can factor them out, factorize that expression there. And what we get after the factorization is this. Basically, after factorizing this cos x there, I brought this limit, I brought it inside and I put it in front of this fraction. I factor these two causes out and put them at the front there, basically. So that's what you see in the line below. And I wrote another limit as h approaches 0 here, because this expression you should be familiar with by now. It approaches 1, my bad. So this approaches 1 here, and the red expression approaches 0. So what we end up with is basically the derivative of cos being negative sine of x. Now, if you like to pause the video and confirm and validate this for yourself, please do so. Maths is learned by validation, by read for yourself. Just before I leave you to get on with the first exercise, I should point out that there may be a coefficient in front of the angle x or theta or anything like that. So we're going to look at how to deal with the other coefficients being in front of the theta here. For example, sine of k theta. So with the small angle approximations, we can say that any multiplier at the in front, or coefficient in front of theta, will give us the sine of k theta approaching to be k theta as theta approaches 0. So when we use this expression in our work, the thetas will cancel away for sine and the k remains, right? So just bear that in mind. We're going to use that in our proof in a minute. And for cosine, we'll end up with this expression. Now, if you replace that expression 1 minus k theta squared over 2, and the ones cancel away on the numerator, and then we'll have k squared theta squared. Now, one of those thetas on the top will cancel away, with power of 2 will become power of 1 because of the denominator, but the remaining one, we will still have one more theta on top of the numerator with the negative sign and k squared, of course. So finally, when we take the limit and this expression as theta approaches 0 will actually turn out to become 0, because we are multiplying k squared over 2 by theta, which will be 0 here. So multiplying any time by 0 will give us 0 again. So just bear that in mind as we look at the next proof here. So we are going to just take k of x to be our function, sine k of x to be our function, and we are going to replace that in the formula. So from first principles, we'll have something like this. And when we, first of all, we're going to multiply this k into these expressions, because we actually want to separate kh and kx separate into two different parts. So we're going to use the formula on top of the top right hand corner here to get this expression, and then factorize the red bits, the bits that I've highlighted written in red. So once we factor them out, we end up with this expression. When you think about this, the bit in purple will approach 1, actually, sorry, will approach k, and the bits which are circled in blue here will approach 0. So that expression will approach k. So we will have k in front of cos kx. And so from this, we can make some generalizations. So if we have the function itself being, for example, sine of 3x, then we can say the derivative of this function is going to be 3 in front of cos 3x. Remember not to change this input, that remains as it is. Alright, and similarly, if we have a function that is cos of, let's say, 4x, now if you remember the derivative of that, cos was negative sign, but because the input has a 4, we are going to bring that 4 out and have a negative sign in front of it before we write sine of 4x there. Alright, so with that, my first lesson is over. So I can make some more generalizations here, which are very useful. You can tell that when we differentiated sine, we got cos, and when we differentiate cos, we got back negative sine. And if you write these for yourself, sine, its derivative will give us cos, cos will give us negative sine. Because of the minus sign in front, that will give us negative cos again. And once more, if we differentiate the negative cos, the negative and a negative will cancel each other out and take you back to top of the line here. So there seems to be a recursive uh, formula which I use for integration as well. Anytime we integrate any of these functions, there is no need to use any of these proofs. From now on, you can remember that the integration of sine will give us negative cos, the integration of negative cos will give us negative sine, and negative sine will give us cos, and so on. So just remembering the first four terms of this column here will be very helpful for both differentiation and integration. And we remember that uh, if we have a constant in front of the input, the angle, then that coefficient will come out at the front. Okay, so I suggest you have a go at least every other question from exercise 9a, and I'll see you in the next video.